My name is Daniel Apwith-Olani, and I am project lead for the SMC Clean project. SMC Clean Module 3.4 covers LID and GSI maintenance, Chapter 4, and the SMC Clean LID and GSI Construction, Inspection, Maintenance, and Monitoring Guidance Manual. An overview of LID and GSI maintenance. Proper maintenance of LID and GSI measures is important to ensure that these systems continue to function as they were designed. Performing effective maintenance of LID and GSI measures on a regular basis ensures continued proper function, meeting performance standards associated with their design, and providing pollutant removal and hydrologic benefits. There are, however, maintenance challenges. Maintenance of LID and GSI measures can present significant challenges that should be considered with the installation of LID and GSI measures and in planning for maintenance of existing measures. That includes maintenance training. Proper education and training of maintenance staff and crews is an essential to proper function of LID and GSI systems. Maintenance training continues to be a significant challenge as some maintenance staff and crews may not be familiar with the LID and GSI measures they're tasked with maintaining. An effective and consistent training of maintenance personnel will help ensure long-term functionality of LID and GSI measures. Another maintenance challenge is related to the nature of LID and GSI measures as distributed systems. An increased number of LID and GSI measures within a jurisdiction can strain existing municipal budgets for both maintenance of LID GSI measures in the public right-of-way and on inspections of LID measures in both the public and private right-of-ways. LID and GSI measures are designed to manage stormwater resource, and because of the LID and GSI approach, a large number of smaller systems are integrated into specific drainage areas as opposed to small numbers of regional BMPs. An increased number of the smaller LID and GSI systems results in an increased amount of maintenance responsibility and increased costs associated with that maintenance. Additionally, more LID GSI measure inspections need to be performed. Education and training of inspectors is yet another challenge, as some inspectors may not be familiar with LID and GSI BMPs and need to be trained for different levels of inspections. Untrained inspectors may not be able to identify different types of BMPs of LID and GSI measures and how they function. If inspectors cannot understand the LID and GSI BMPs during construction, the measures may not be identified as incorrectly constructed. This may affect the ability to perform proper maintenance in the future. Some inspectors may not understand different LID and GSI maintenance triggers, which results in ineffective inspections and poorly maintained LID and GSI systems. There are specific maintenance issues as well, and those include vegetation management. We can see overgrowth in barren areas in GSI systems, as well as dying or dead vegetation, as well as there may be issues with identification of the types of vegetation and what should stay and are part of the system and what should be removed as part of maintenance. There are also erosion issues. Lack of energy dissipation within a system can cause erosion within a system. Replacement of additional plants may be needed, and the BMP may be brought online before plants become established, which can cause erosion within a system. Additionally, sash and sediment and trash accumulation can be an issue. Those can block inlets and can also reduce the capacity and clog systems. Maintenance and information tracking is also an issue for LID and GSI systems. As the number of LID and GSI measures increases, the maintenance increases, and then also the time and effort needed to adequately track the LID and GSI maintenance increases. Tracking of maintenance should include maintenance action that was performed, evaluating and understanding what exactly was done. Was it vegetation removal, sediment removal? And then also quantification of that maintenance action. So identifying and quantification of the volume of sediment removed, for instance. And then finally, tracking the cost to perform the maintenance, including the labor cost and other costs, will be helpful in planning for future maintenance of those systems. Now I'm going to move on to specific maintenance for bioretention systems. As far as general maintenance goes, that includes inspection and observation of inlet and outlet structures, side slopes, and bioretention inverts. You're evaluating erosion, if the existence of burrows or emergent trees or woody vegetation are present, and looking for graffiti or vandalism, and if there is a fence, if there's any damage to that. General maintenance should consider proper and timely maintenance that is essential to continuous and effective operation. All structural components should be inspected at least once annually for cracking, subsidence, spalling, erosion, and deterioration. Components expected to receive or trap debris should be inspected for sediment. Sediment removal should take place only when the system is drained and when it is dry. The disposal of debris, trash, and sediment should be done so in a suitable disposal location. Maintenance frequency should be at least annually or after rain events of 3 inches or more for Southern California locations. Maintenance indicators include standing water 96 hours after a storm event, burrows, holes, or mounds, debris or trash present, sediment, and then the sediment depth exceeding 10% of the facility design capture. Recurring conditions in a bioretention system after significant storm events, such as sediment accumulation, may indicate that there's not an issue with the bioretention system itself, but that the drainage area of the bioretention system needs stabilization. Drainage time is another maintenance concern. Specifics about drainage time include that the bioretention system must be inspected at least annually to determine if the infiltration or biofiltration capacity in the basin is decreased. Ponded water and drawdown failure can be caused by crusting or sealing of the soil surface, heavily compacted soil, large amounts of sediment accumulating in the soil, or blocked or clogged overflow structures. If the bioretention system fails to drain in the design storm within 96 hours, consider removing excess sediment and removing dead and excess vegetation. If that doesn't work and it still fails to drain, you can pump the water and use that for non-potable use, flush the bioretention system cleanouts and ports if they are available, such as the inner drains, and if that doesn't work, you can replace the top 2 to 3 inches of BSM for the entire bioretention area. Trash and debris accumulation is also an issue as far as maintenance. That can clog or inhibit the infiltration or biofiltration capacity and clog overflow structures, which can cause extended drawdown times and unwanted ponding, overflowing, and flooding. Specifics about trash and debris guidance include the following. All trash and debris should be removed from the bioretention system before the start of the rainy season of October 1st and as frequently as site conditions are necessary. All materials should be discarded in an appropriate facility, and the maintenance indicator for trash and debris is excessive debris or trash present when trash could inhibit the capacity and function of the bioretention system. Sediment management is also an issue for bioretention maintenance. Some sediment accumulation in bioretention systems is normal and expected. Excess sediment in bioretention systems reduce their capacity and could cause clogging. Specifics about sediment management guidance include the following. Removing sediment accumulation on an annual basis or more often as needed. You're replacing damaged vegetation as a result of removal of sediment in bioretention systems. And you're investigating the source of excess sediment in the drainage area if you have problems with stabilization. The maintenance indicator is sediment depth exceeds 10% of the bioretention system design or the drain time exceeds 96 hours. Bioretention maintenance also includes bioretention soil media repair or erosion control. Inflow of water movement through the bioretention systems may cause erosion and scouring of the BSM surface over time. Erosion and subsequent sediment deposition can be detrimental to the filtration capacity of the bioretention system, cause damage to plants, and create clogging overflow structures. Fixes include repairing measures must include identification and correcting the cause of erosion by repairing the erosion damage or removing sediment created by the erosion process, identifying if erosion is caused by a lack of energy dissipation in the system, if there's any damaged energy dissipation, and if necessary, add energy dissipation and flow dispersal measures. Reseed or revegetate barren spots as appropriate for the area. Remulch as necessary. And your maintenance indicator is erosion on the side slopes or invert of the bioretention system, any rilling that's occurring on the side slopes of the bioretention system, or erosion near inlet or outlet risers. Vegetation management is also a concern within bioretention systems. These are vegetated systems, and vegetation plays an important role in the treatment process and supports infiltration and biofiltration capacity. So it's important to have well-established vegetation for bioretention systems. Lack of vegetation can cause erosion, whereas excess vegetation can degrade bioretention systems, taking up basin capacity. Maintenance practices include cutting and removing vegetation and clippings as appropriate, removing any emergent trees or woody vegetation. Any plant material that blocks the inlet or facility must be pruned, thinned, or removed and disposed of. Removal of excess vegetation that reduces the capacity of the bioretention system must also be completed. And then removal of any dead, diseased, dying, or missing plants must be replaced. Your maintenance indicator is emergence of trees or woody vegetation, and your average plant height is greater than 12 inches. Rodents can also cause a particular issue within bioretention systems. Rodent damage in animal burrows and bioretention systems can cause structural, landscape, and stormwater flow-based issues. Burrows also may create preferential flow paths and short-circuiting through the section of the berm, causing pipe-in and erosion problems in the berm. Rodents can also damage plants and plant root systems. The maintenance practices include, if a rodent or other damage is observed, consult a licensed professional pest control service for eradication, trapping, and relocation as appropriate. Where burrows cause seepage or erosion or leakage, backfill firmly. And your maintenance indicator is visible burrows, holes, or mounds. Structural damage is also a concern for bioretention maintenance. Minor structural damage, components such as bioretention system edges or overload structures should be repaired on a yearly basis. More significant structural damage must be repaired as soon as possible. Maintenance practices for bioretention structural damage include minor repairs, such as patching chips and cracks to concrete structures and resetting outlet structure frames and grates. Major repairs include removal and replacement of damaged overflow risers, structural bracing, and supplemental reinforcement of failing structural components. Maintenance indicators include minor and major structural damage, and then you should be inspecting after all earthquakes of magnitude 5 or higher, or other incidents that may affect the bioretention system. The lifespan of bioretention systems can be up to 20 years and potentially longer if properly maintained. Bioretention lifespans depend significantly on the maintenance of the bioretention system and stabilization of the bioretention system drainage area. More sediment entering the basin equates to a reduction in bioretention system lifespan. Now I'm going to move on to permeable pavement maintenance. So general maintenance includes inspection of the pavement surface, the surrounding areas of the pervious pavement, and the upstream drainage area of the permeable pavement. So as far as maintenance occurring, proper and timely maintenance is essential to continuous effective operation of permeable pavement and prevent clogging. Your maintenance indicators include standing visible water on the pavement for more than 40 hours after a recent rain event, structural damage, and weed growth, sedimentation, vegetation, and other material clogging the permeable pavement surface. Signs of contamination on the permeable pavement surface is also an indicator that maintenance needs to occur. For trash, debris, and accumulation, they can clog or inhibit the infiltration or filtration capacity of the permeable pavement system. Clogged or inhibited infiltration or filtration capacity could lead to unwanted ponding. Maintenance practices include for prior to the wet season, all large trash and debris should be removed from the permeable pavement system, and materials should be discarded in an appropriate facility. Large trash and debris should be removed before sweeping or vacuuming. Smaller trash and debris can be removed by routine vacuuming. Rakes and leaf blowers can be used to remove leaves. Your maintenance indicator is excess debris or trash present to where the function of the permeable pavement could be affected. Vacuuming. So vacuuming is an adequate way to maintain your permeable pavement system. Sediment and smaller debris accumulated on the permeable pavement can clog the surface and prevent stormwater infiltration or filtration. As far as vacuuming actions, after large trash and debris have been removed from permeable pavement surfaces, the system should be vacuumed to clear all sediment and other debris from the pavement surface. Prior to vacuuming, remove bulky debris, waste materials from the pavement surfaces that are too large to be picked up by the vacuum. Vacuum sediment and debris from the entire surface area of the permeable pavement installation using a dry vacuum. Give extra attention to the pavement edges where you can get accumulation of sediment. Sweep up sediment and debris from surrounding surface areas, especially those that slope toward the permeable pavement. You're going to note any report or damage in the pavement, including holes, cracks, excessive scuffing, settlement, and areas of standing water. And then you're going to vacuum the sediment and debris from upstream or highest point to downstream, the lowest point, to prevent any sediment from being carried onto the vacuum surface. Your maintenance indicator is surface ponding of greater than 48 hours after a rainfall, excess sediment, or other material logged in the voids of the permeable surface. Finally, pressure washing and restorative vacuum are an essential element for permeable pavement maintenance. Over time, deep cleaning and unclogging of permeable pavement may become necessary and is best accomplished by simultaneous pressure washing and restorative vacuuming. The elements of pressure washing and restorative vacuuming maintenance include not using extremely high pressures with a pressure washer that can dislodge joint aggregate and unit pavers and damage pervious concrete and porous asphalt surfaces. Prior to vacuuming, you're going to be picking up all and remove bulky debris and disposing it in an appropriate location. Vacuum and pressure wash impacted areas of the permeable pavement, dispose of sediments and debris in an appropriate facility, and note and report any damage in the pavement, including holes, cracks, excessive scuffing, settlement, dislodged aggregate, and areas of standing water. After you're done vacuuming and pressure washing permeable pavers, rejoint the pavers with the appropriate aggregate base on the original design of the paver manufacturer's recommendation. Your maintenance indicator is extended surface ponding of greater than 48 hours of rainfall, excessive sediment, or other material lodged in the void of the permeable surface.